Good morning, everyone. Yeah, today we will talk about new topic called current and resistance. Actually, we have already talked about about the electric. We talk about the electric charges, atoms, Coulomb's law. Yeah, like the relationship between the charge and the electric field, and how to calculate the electric field based on the charges. And also we talk about it electric field and the electric forces. What's the relationship between the electric forces and electric fields, and how to calculate them. And then we talk about the electric potential. Yeah, what is electric potential? What's the relationship between the electric potential and the electric field? Also, we talk about the electric potential generated from a single point or a point charge, and also electric potential generated from the uh, parallel plates like capacitors. And yeah, we talk about those all about the electric things. And today we will also focus on the electric content things like called current and resistance. Actually, I think you guys must have heard about this, like current, resistance, and voltage. Actually, we have already talked about the voltage. The voltage is just like the electric potential differences. Yeah, we have already talked about that. It's just a different name for voltage. In the real world, we usually call the electric potential difference like a voltage. And actually, yeah, and also we talk about like current and resistance more often than other things. In the today we will talk about what is current, what is resistance, and how to calculate them, and what's the relationship between the current and the electric field or electric potential difference. Yeah, okay, let's uh share my screen. Yeah. Yeah, today we will talk about the current and resistance. And like for the chapter 22, yeah, what's the chapter's goal? We mainly focus on learning how and why charge moves through a conductor as a current. Yeah, we will try to understand those things, like how and why charge moves through a conductor as a current. Okay. Let's do a preview for chapter 22. Yeah, firstly we will talk about the current. Yeah, and uh speaking of current, what is the first thing you can think? Actually, yeah, you will think the bright bulb, and you will think some like shining lights. Yeah, actually the motion of charge through a conductor, like the wires connecting these lights, is called a current. Yeah, you can see the current, actually it is the motion of charge through a conductor. Yeah, the current seems is a moving. Yeah, it's a motion of charge. And we will learn that why conservation of current ensures that each bomb is equally bright. Yeah, you can see, although those small bombs have different colors, but actually they are equally bright. Yeah, we will talk about why. And then we will talk about resistance and Ohm's law. In the yeah, the Ohm's law relates the current in this bulb to the battery's voltage. Yeah, I talk about the voltage is what, like the potential electric potential difference, and the bulb's resistance to the flow of charge. Actually, the Ohm's law, yeah, just represent the relationship between current, voltage, and resistance. And yeah, and I will talk about what is resistance later. Yeah, you will learn how to relate the resistance of a wire to its size and composition. Okay, yeah, and then we will talk about electric power. Yeah, the hair dryer, yeah, you use it often, am I right? Yeah, converts electric energy to thermal energy. You can see how can we get like a heat thing. Yeah, we just convert the electric energy to thermal energy, leading to a blasting of hot air. Yeah, and yeah, we will learn the relationship between electric power to current, resistance, and voltage. Yeah, yeah, this is main content in chapter 22. Yeah, before we start 22, let's do like a looking back thing. Electric potential and electric field. Yeah, this is what we talk about in uh, last chapter 21. Yeah, in section 21.5, you learned the connection between the electric potential and the electric field. Yeah, in this chapter, you will use this connection to understand why charges move in conductors. Yeah, actually, this chapter based on the last chapter. Yeah, and we will learn uh, like a why charge moves in conductor. Yeah, and the electric field always points downhill. Yeah, from higher to lower potential. Yeah, we talk about in last class. Actually, you can see this is the electric field. Yeah, the electric field always like a point, points downhill from the like a higher potential, because this is the positive, this is the negative or zero. The negative also the lower. Yeah, go to the lower. For example, it is like a negative 100 volt. Yeah, it is lower from higher to lower, as in this parallel plate capacitor. Yeah, this is what we talk about in last class. In this class, we will talk about like the current. Actually, the current is just a charge move, the motion of charge. Yeah. Okay. Before we talk about that, let us think about this question. An electron. What is electron? We know the electron and the proton. And electron is just a negative E. This is E. The proton is E. That makes sense to you? Yeah. I think you must remember that, because this is from like uh, last class content. Yeah, and uh, like an electron is released from the right at the dot. Yeah, at the this is the initial position, and it is released from the dot, and afterward the electron A starts moving to the right, this way, or remains at rest. We know like the electron, it is negative charge. Am I right? Yeah, it's negative E. So since it is negative, it should go to the positive charge. Does it make sense to you? Yeah, and the positive is like the like electric field. It always point to the from the higher to the lower. Yeah, and actually it this electron will go to the higher potential. Yeah, because electric potential, because this is a negative, it will goes to the positive direction. Does it make sense? Because the two like a opposite like a charge will have the attractive force. That makes sense to you? Yeah. So then the question should be start moving to the right. Then the answer should be start moving to the right, because this electron will go to the positive charge. That makes sense to you? Yeah. Let's check. Okay, this is today's goal. Like firstly, we will understand a model of current, and then we will study how to define and describe current. And finally, we will learn batteries and EMF. Yeah, what is EMF? We will talk about that later. Okay. Firstly, let's talk about a model of current. You can watch this video to understand like a current and resistance. Yeah, I will now play it in the class. Okay, yeah. For the model of a current, if we connect two capacitor plates of a parallel plate capacitor with a metal wire, yeah, this is like a the negative parallel plate capacitors, and this is positive And actually, if they didn't connect, and this is like the positive Q, this is a negative Q, and they will remain like a stable condition. And but if we connect those two with like a wire, a metal wire, actually the plates become neutral. Yeah, because you can see, and this positive and the negative will be neutralized, and the capacitor has been discharged. Yeah, that makes sense to you? Because the net charge of each plate is decreasing, because the negative and the positive will be neutral with each other. Yeah, that makes sense to you? Yeah, this wire is a conductor. Yeah, because it's metal wire, a material through which this is a material through which charge easily moves. Yeah, this charges will easily moves, and then it will be neutral, and those plates will become neutral after like those two parallel plate capacitor with a metal wire. Yeah, does that make sense to you? Okay. Yeah, the motion of charge actually after you connect those two plate, the motion of charge, yeah, through a metal, we call it a current. Yeah, there will be like a motion of charge. Yeah, if we observe a capacitor discharge, we see other effects. As the capacitor discharges, the connecting wheel gets warm. Actually, you can do these experiments like yeah, in our campus lab. In our campus lab, if you connect the capacitor with a negative and a positive, like and with a wire, and you will see like the connecting wire gets warm. Yeah, we will talk about why. What's the reason for this situation? As a capacitor discharges, if the wire is very thin in places like the filament of a light bulb, yeah, you can see there. If you observe a light bulb, and there are some like filaments, yeah, inside it, yeah, and this filament is very thin, yeah. The wire gets hot enough to glue, yeah, like which means yeah, we will talk about why. Yeah, we will leave this question here and talk about it later. Yeah, more current means a brighter bulb. That makes sense to you because more current, yeah, means the charge through this bulb is more. Am I right? So and then the like a bulb will be brighter, which like more current means a brighter bulb. Yeah, I think this is easy to understand. Am I right? Yeah, a light bulb glows, and the light bulb like a filament is part of the connecting wire. Yeah, this is part of the connecting wire. Yeah, and as a capacitor discharges, the current carrying wire deflects a compass needle. Yeah, yeah, this is also like because there is the compass needle is deflected because the motion of charge, because the motion of charge, and also because of the current. That makes sense to you? Yeah. Okay. You can also check these videos for like effects of a current. Yeah, we will. Yeah, this is one effect is just like the the like the bomb will be bright, and the wire will be hot, and the compass needle will like will move. Yeah, which means that the move means kinetic energy. Am I right? The like light means bright means like thermal like energy, and the hot also like the thermal energy. Yeah, we will talk about it later. Yeah, this is about a conversation of conservation of energy. Yeah. Okay, let's continue to talk about a model of a current. Yeah, the charges that moves in a current are, are called charge carriers. Yeah, the charges that moves in a current, we call it charge carriers. In a metal, the charge carriers are electrons. Yeah, you can see. This is all else, and the metal atoms minus the conductor electrons, o, o, occupy fixed position, and the conductor electrons, generally a few per atom, are bound to the solid as a whole, not to any particular atom. They are free to move around. Yeah, those electrons are free to move, but these like atoms, yeah, they just occupy fixed position. They don't like move easily, but these electrons are free to move around. The metal as a whole is actually it's electrically neutral. If you can see, if the metal wire that doesn't connect to like a circuit, actually it's neutral. Like it's not like positive or negative. Yeah, it's neutral because the negative and the positive and negative charges are equal. Yeah, only like the positive charges occupy the fixed position, but the neutral electrons, like negative charges, they can be free to move. Yeah, this is the motion of the conductor electrons, which are free to move around. That forms the current in the metal. Yeah, if actually, yeah, when you connect to the wire, when you connect the like this like charge carrier charge carrier to a circuit, and then there is a like a specific direction current through the wire. It doesn't make sense to you. Okay, let's continue to talk about the model of current. An isolator does not have free charges and cannot carry a current. Yeah, this is just the features for current. You can see an isolator, the it doesn't have free charges and cannot carry a current. You can see if you connect the metal wire in the circuit, it has a current. But if you connect some like clothes, some like paper, yeah, and there is no current, that makes sense to you if you do some labs about that. Yeah, because the isolator does not have free charges. Yeah, other materials may have different charge carriers. Both positive and negative ions carry charge in ionic solutions such as seawater, blood, and intercellular fluids. Yeah, different materials actually they have different charge carriers. Yeah, we will talk about this later more. Yeah, okay. Let's talk about creating a current. Yeah, suppose you want to slide a book across a table, and you give a quick push, it starts moving, but it begins to slow down because of friction, leaving the book and the table warmer. Yeah, you can try to do this small lab by yourself. Yeah, the only way to keep the book moving at a constant speed is to continue push it. Yeah, this is obvious. If you want the book like moving continuously, you need to continue pushing it. Something similar happens in a conductor. Actually, something, yeah, you can see there the collisions reset the motion of the electron. It then accelerates until the next conclusion. Yeah, you can see the electron has a net displacement opposite to the electric field. Yeah, this one will meet like have the conclusion with this proton, and then get a new direction to the other one, and then to the other one is the other one. Yeah, this is kind of like a electron moves. Yeah, but we know like you need to give the give it a continue pushing force, then it will like move. Does that make sense to you? Okay. When we apply an electric field to a metal, yeah, the field exerts a force on the electrons and they begin to accelerate. Yeah, like we talk about this. If you want to like keep the book moving, you need to push it. And if you want to the electrons moving, you need to create an electric field. Yeah, because this electric field can give the electron force. That makes sense to you? Yeah. And conclusions between the electrons and the atoms of the metal slow them down. Yeah, this makes sense. If you, this electron field just make the electron like a electric field just make just give this electron a force, let them move. But if they like hit the atoms and they will slow down. Yeah, transforming the electrons kinetic energy into thermal energy, making the metal warmer. Yeah, that's the reason why like if you connect a wire to a circuit to a power and the wire will be warm because this heat like these electrons hit the atoms, yeah, will make the will like a transform the electrons kinetic energy into thermal energy, making the metal warmer. Does make sense to you? Yeah. Okay. The motion of the electrons will cease unless you continue. I think there is a pushing, continue pushing by maintaining an electric field. That makes sense to you? Because if the force disappear, yeah, the electron will not like will cease. Yeah, and if you want the electrons keep moving, you just like need to continue push it like by maintaining an electric field. To maintain an electric field, we need a potential differences. Yeah, then we talk about this in last class. A potential difference. How can we get that? Yeah, there are two different ways. One is a battery. Am I right? And the other is like a parallel plate with charges. Yeah, do you remember that? So which means like that's a reason why a battery can maintain can like give can make a current. Does it make sense to you? Yeah, in a constant field, an electron's average motion will be opposite the field. Yeah, you can see this is the electric field. Yeah, which electric field usually it is like from the positive to the negative. And then like the because these electrons will attractive by the positive, so it will move the opposite. Yeah, opposite is the field. The motion is electron. The motion is the electrons drift velocity. Yeah, we just call this motion is the electrons drift velocity. That makes sense to you? Okay. Like in a parallel plate capacitor, the initial separation of charges creates a potential difference between the plates. Yeah, we talked about this in last class. Connecting a wire between the plates establishes an electric field in a wire, which causes electrons to flow from the negative plate, which has excess of electrons towards the positive plate. That makes sense to you? Yeah. We talk about actually you can see this is a capacitor plate, this is the other. If you connect with a wire and then the electrons, yeah, because usually the atoms will like have the fixed position, the electrons will like move from the negative plate to the towards the positive plate, then the current generate. Yeah, does it make sense to you? Yeah. And the potential difference creates the electric field that drives the current in the wire. Yeah, because the potential difference creates the electric field that drives the current in the wire. We talk about it later, just now. Yeah, eventually the plates will be completely discharged, meaning no more potential difference, no more field, and no more current. Yeah, you at the beginning, because there is like a potential difference. Yeah, from maybe positive 10 to negative 10, so it is 20-volt differences. Yeah, and then as the electrons moves, and they will be neutral, and there will be no more electric potential difference, no more field and no more current. That makes sense to you? Yeah. This process we call it the capacitor discharge discharging. Yeah. And yeah, this is the process of how to use the capacitor to generate the current. You can see because the wire is this is a higher potential. This is a lower potential. Yeah, because the wire is connecting between 2 points of different potential. There is electric field. Yeah, the electric field is like from the positive to negative, and then the the electron is the opposite direction. Yeah, and which pushes this electric field pushes electron through the wire to this one, and then be neutral. So this process is like we call it a capacitor discharging. That makes sense to you? Okay. Okay, let's talk about the conservation of current. Actually, you can see the current at point B, this point, is exactly equal to the current at point A. Actually, no matter B is here, or B is here, or A is here, or A is here, actually the current in this whole wire, like this wire, in this wire and this wire is exactly equal. Yeah, the current leaving light bulb is exactly the same as the current entering the light bulb. Yeah, like this current through this wire and this through this wire. And also the current through the bulb is exactly equal. Yeah, the light bulb cannot destroy electrons without violating the law of conservation of mass and the law of conservation of charge. Yeah, actually the light bulb, yeah, they cannot it cannot destroy electrons, yeah, without violating the law of conservation of mass and the law of conservation of charge. Thus, the number of electrons is not charged, it's not changed by the light bulb. Yeah, the number of electrons, yeah, here, the electrons through the bomb, and this bomb cannot change, cannot destroy the electrons. It's just let the electrons go through it. Yeah, the number of electrons is not changed by the light bulb. The light bulb cannot store electrons, or it would become increasingly negative until its repulsive force would stop the flow of new electrons, and the bomb would go out. Yeah, actually, you can see the light bulb also cannot store electrons. It will become increasingly negative until its repulsive force would stop the flow of new electrons, and the bulb would go out. Like, which means you can see this is the capacitors. After the capacitors goes to the neutral, yeah, there is no electric field through here. Yeah, and which means mm, the bulb would go out because there is no flow of electrons if there is no electric field. Yeah, every electron entering the bulb is matched by an electron leaving the light bulb. Yeah, which means the electrons go through from here to here, and then come out from the bulb. Yeah, it just goes through the bulb, and and thus the currents on either side of light bulb are equal. Yeah, doesn't make sense to you. Yeah, because the the current is just the motion of charges, and you can see the charges are same from like a before going to the bomb or after get out from the bomb. It's the same charge, same number of electrons. So which means the current is same. That makes sense to you? Okay. Like with an electric current and a light bulb, water flows through a turbine, making it turn. Yeah, you can see here there is a water flow, and this water in the water flow through a turbine and make this turn. Yeah, it's just like electric current. We can call it like a water current. The amount of water leaving the turbine equals the amount of water entering the turbine. Yeah, you can see the water amount water goes into it just equal the water goes out to. It's just similar with the flow of electrons. This is the flow of water. Yeah, flow of water and this flow of electrons. The amount of water leaving the turbine equals the amount of entering. Is like similar. The number of electrons leaving the bomb equals the number entering. Yeah, this is just like the conservation of current. Yeah, the water, like an electric current, is doing work, so there is an energy change. Yeah, you can see this water can is doing the work like make the turbine running. Yeah, so there is a energy change. In a light bulb, the energy is dissipated by atomic level friction as the electrons moving through the wire, making the wire hotter until it glows. Yeah, so we have our first conclusion, law of conservation of current. The current is the same at all points in a current carrying wire. Yeah, that makes sense to you. This is the law of conservation of current. And let's check some quick check questions. A wire carries a current if both the wire diameter and the electron drift speed are doubled. The electron current increases by a factor of. Yeah, actually, you can see the wire diameter and the electron drift speed are doubled. Yeah, we know the current is a motion of current, motion of charges. And yeah, we will talk about the equation in next class. Yeah, but you just have the initial idea like how the relationship between the current and the wire diameter and the electric drift speed. Actually, the current depends on the like speed and the area, the wear area. You can see if you are familiar with the electric thing in the real world, you can see the thick wear can go through more current. That makes sense to you. So actually, the current depends on the like electron speed and the wear like area. Yeah, the area is just like a square diameter. Am I right? So which means if this is double, and the current will four times, and the speed is just if it is double, it will two times, and two and multiple four, it will be eight. Yeah. So in this, the answer should be eight. In this like a question, you just remember like the current actually it depends on the where diameter and the speed. Yeah, the speed, the electron speed and the where diameter will affect the current. Yeah, we will talk about the details in next class. Okay, let's talk about one conceptual like example. Which bulb is brighter? Yeah, the discharge of a capacitor lights the figure. Yeah, you can see this figure. This discharge of a capacitor lights two bulbs. Compare the brightness of two bulbs. Yeah, current is conserved. So any current that goes through bump one must go through bump two as well. Yeah, we talked about just now. The currents in the two bumps are equal actually. Yeah, which means the breadth is same. Am I right? The brightness is same. Current is conserved, so any current that goes through bump one must go through bump two as well. The currents in two bumps are equal. We've noticed that the brightness of a bump is proportional to the current it carries. Yeah, actually, the brightness of a bump is proportional to the current it carries. More like a current, like it will brighter. Yeah, identical bumps carry equal currents must have the same brightness. Does it make sense to you? Okay. Yeah, this result makes sense in terms of what we've seen about the conservation of current. No charge is used by either bump. Yeah, it's just like this electrons just go through to bump. Yeah, that makes sense to you. Okay, let's talk about the other topic. Define how to define and describe current. Okay. Yeah, like we talk about a capacitor discharges in the same way, whether we consider negative charges moving opposite the field or positive charges moving in the same direction as the field. Actually, we know like we talk about the parallel plate discharges. It's as a negative charge enters this well and yeah, the like electrons, the positive, the negative charges enters this like positive like plate and cancels its positive charge. Yeah, this is like a capacitor discharges. Yeah, also we can like consider the positive charges like goes to the negative plate and then like neutralize these negative charges. Yeah, this plate discharge as positive charge enters and cancel its negative charge. We can consider like the discharge process as this one. Yeah, actually, the in the real like situation, it's just the electrons like goes through from this one, but it's a same situation. Like if we understand the current is the discharge process as this one. Yeah, but this one like is easier to understand for us. So like we adopt the convention that the current is the flow of the positive charge. Yeah, we just like when we analyze the current, we just like adopt the convention that the current is the flow of positive charge. Yeah, like the positive charge flow from the positive plane to the negative plane and then do the neutralization. Yeah, it's a yeah, we just like consider it is the real situation. Yeah, and to this like a convention will help us to easy to analyze the current and the circuit. Yeah, we will talk about, we will see it later. Yeah, okay. The currents are charges in motion, so we define current as a rate. Yeah, we know that like the current is the motion of charges. Yeah, the charges in motion, so we define current as a rate. Yeah, in kilometers per second. Yeah, this is a C per second. This is a unit for the like a current, and which charge moves through a wire. Yeah, like per second. How many charges go through this wire? Yeah, we just define this the current. You can see the we use I to like represent current usually. Yeah, the current I is due to the motion of charges in the electric field. Yeah, and we imagine an area across the wire through which the charges move in a time, in a small time, like delta t. Charges delta q moves through this area. Yeah, we just like uh, uh, imagine there is an area like across the wire. Yeah, and in the delta time, charges q moves through this area. Yeah, then we move then we define. Yeah, we measure the amount of the charge delta q that passes through a cross section of wire in time interval like delta t, then the definition of the current, we use this equation like uh, the current equal how like in a short time, like how much the charges go through. Yeah, that makes sense to you. This is the definition for the current. Right. Yeah, the current direction in a wire is from the higher potential to a lower potential. Yeah, which means it is the current direction, like in a wire, the higher position, which means the higher like position, like position energy. Yeah, and the lower potential, which means the lower potential energy. Yeah, uh, yeah, all like in the direction of the electric field. Yeah, in the direction of electric field. But do you remember when we talk about at the beginning, we talk about the electrons usually go opposite of the electric field. But here we talk about it's the direction. Uh, yeah, the direction is like it's just the direction of the electric field. Do you know why? Yeah, we just talk about it. Yeah, actually, in the real situation, the electrons moves, yeah, from the negative plate to the positive plate. But for the convenient for our for the easily calculate for the easy calculation, we just consider like it is the positive charges go through the wire to the negative plate. Yeah, we just adopt this conversion. Yeah, so that's the reason why the direction here is just the current direction. When we talk, we like define the current. We just define the current direction is the same direction of the electric field. Yeah, that makes sense to you. Yeah, just yeah. Current is measured in coulombs per second. Yeah, like a C per second, which we define as an ampere. Yeah, A. Yeah, we shorted it. Actually, this is like a gas name. Yeah, a scientist name. Yes, scientist. Yeah, this like a scientist found the current, so we just use his name as a unit for like current. Actually, the real current unit is C per second. Yeah, 1 ampere is equal 1A. Yeah, it's just a short name for this one, and equal 1 coulomb per second. One just short for 1 C per second. Household current are typically 1 ampere or one. Yeah, just this is our household current, like a big how much of our household current usually is 1A. Yeah, for a steady current, the total amount of charge delivered by a current I during time during time interval delta t is this one. Yeah, because you know we know that I equal delta q divided delta t. Am I right? So which means the total amount of charge delivered in this time delta q equal I delta t. Yeah, yeah. This charge is just a total amount of charge delivered by a current during this time. Yeah, does it make sense to you? Okay, let's review some quick chat questions. And every minute, 120 signal charge flows through this cross section of the wire. So the wire's current is, we know like the current equal what? I equal delta Q and delta T. Here, delta Q is 120, 120, and every minute, which means 6 seconds. Am I right? 16 seconds, which means it is 2A. That makes sense to you? So the answer should be D. Yeah, yeah, we just use this equation, yeah, to calculate it. Okay, and let's talk about this example, like a charge flow in a light bulb. 100 volt light bulb carries a current of this 0.83 amp. How much charge flows through the bulb in 1 minute? Yeah, how much charge? Uh, like uh, uh, flow through in 1 minute. And when the equation 22.2 is given the charge in terms of current and the time interval, like the charge equal I delta t, am I right? So here, according to this equation, and we can calculate the total charge passing through the bulb is I equal this one, it has a current, and t is 1 minute is 16 seconds. So the this is like charges flow through, yeah, in 1 minute. Yeah, and yeah, let's assess this mm, result. The current corresponds to a flow of a bit less than 1 C per second. Yeah, you can see here. And it is smaller than 1A. Yeah. And so our calculation seems reasonable, yeah, because the household we know like it's around 1A. But the result is still somewhat surprising. That's a lot of charge. You can see the charge is 50 C, am I right? It's a lot. Yeah, the enormous enormous charge that flows through the bomb is a good check on the concept of the conservation of current. If even a minuscule fraction of the charge stayed in the bomb would become highly charged. For compression, a Van de graphic generator develops a potential of several hundred thousand volts due to an excess charge of just a few μc, a 10 millionth of the charge that flows through the bulb in 1 minute. Light bulbs do not develop a noticeable charge, so the current into and out of bulb must be exactly the same. Yeah, actually, yeah, even there is a highly charged, which yeah, if you touch the bulb after like it works for like 1 hour, you will like it will hot. Yeah, which means even the current is small. Yeah, but the charge through the bulb uh is not small. Yeah, it can then those current can be transformed to like a thermal energy, which makes the bomb hot. Yeah, we will talk about this later. Yeah, let's talk about this example problem. The discharge of the electric air can transfer a charge of 1.0 MC in a time of 2.0 milliseconds. What current in A does this correspond to? Yeah, I think this is quite easy. Yeah, because we know I equal the Q delta Q divided delta T. The delta Q is MC 2 MC, and the time delta T is 2 ms. So which means it is 1A. Yeah, that makes sense to you. Yeah, I will leave this to you. You can recalculate this. If you have any questions, let me know. Okay, let's view the other quick check question. A and B are identical light bulb connect to a battery as shown. Yeah, there is which is brighter. I think this one is easy. We know like the charge goes through those lines are same. Am I right? So which means the current in those is everywhere are all same. So which means the bulbs are equally bright. Yeah, we talked about this before. This is based on like a conservation of current. Okay, let's talk about conservation of a current at a junction. Yeah, a junction is a point where a wire branches. Yeah, you know, like in the real world, like the like current the circuit is very complicated. It's just not like one wire, just like this, yeah, battery to like a just like let a bomb. This is quite easy, quite simple like circuit, but in the real world, and the circuit is very complicated. There will be many junctions. Here is just some like simple junctions. Yeah, a junction is a point where a wire branches. You can see, yeah, one wire will branches in will like divide into like a this is a junction. For junction, the law of conservation requires like all the input current equal all the output current, which means this is the input current. The input current must equal the output current. This is I1 output, this I2 output, and the input should equal those two plus together. Yeah, and also this is the other one, like this is two input, like I1 input, I2 input, and there is only one output, which means the I1 input plus I2 input equal I output. Yeah. For junction, we need to obey the law of conservation. Yeah, the basic conservation statement that the sum of the currents into a junction equals the sum of the currents leaving. Yeah, this we call it Kirchhoff's junction law. Yeah, I think maybe you have already heard this. Yeah, actually, this Kirchhoff's junction law is very important for us to analyze the circuits later. Yeah. Okay, let's review these quick check questions. And the wires showing next carry currents as noted. Read the currents I, IB, and IC. And this question let us find the relationship between IA, IB, IC. Just remember, no matter how complicated like a circle you met, you just use this junction like a law, like a kickoff junction law. Yeah, just like a check a junction one by one. Here there are two junctions. Yeah, the first junction is here. Yeah, in this junction we know like the input equal the output. So IA should equal to A plus IB. I'm right? Yeah, which means the IA must greater than IB. That makes sense to you? And for this one, the IA input should like I input should equal I output. The input is IB plus 3A equal what? IC. Yeah, the output is IC, which means the IA equal 2A plus IB. The IC equal IB plus 3A, which means IC greater than IA. That makes sense to you? Yeah, the IB is the smallest one, and then the IC is the biggest one, and then the IA is the second one. The IC should greater than IA, greater than IB, so the answer should be C. Does it make sense to you? So no matter how complicated like a circle you met, just use this Kirchhoff junction law, like analyze one section by one section, one junction by one junction. Yeah, that makes sense to you. Okay, let's talk about this one. Okay, this is the answer. Yeah, this one. The current in the fourth wheel is what? Yeah, this question asks us what's the current? Sorry, this current. What's the current for this direction? We know like using Kirchhoff's junction law, I in should equal I out. Here, what is I in? This one and this one. Am I right? Yeah, we cannot like draw this one because we don't know this one is I in or I out. Here, the I in, at least what we observe is I in. Yeah, I in equal 5A plus 2A equal 7A. Am I right? And here there is out 9A. This one greater than this one, which means it should be because the I in should equal I out. Am I right? So which means there is another I in. Yeah. Otherwise, the kickoff like ejection law doesn't apply, doesn't work. Am I right? So which means there is another I in it is equal to a to this direction, and then 2A, 5A, and can have the non-A output. That makes sense to you. So which means there is a 2A to the left. Yeah, the answer should be D. Does this make sense to you? Yeah, this is like we based on the conservation of current, like Kirchhoff's junction law to calculate this. And okay, let's see this example, like currents in a junction, like four wires have currents as noted in the figure. What are the direction and the magnitude of the current in the fifth wire? Fifth wire. Yeah, this is one, two, three, four. And let's talk about like here we know like according to Kirchhoff's law and I in should equal I out. And for now, like the I in, this is I in, this is I in. So I in equal 3A plus 4A equal 7A, and I out for now equal what? This one and this one is 2A plus 6A equal 8A. And we want to let the in equal out. So which means there should be another in equal 1A. That makes sense to you? Yeah. So this, which means the fifth is this direction and the magnitude is 1A. Yeah, that makes sense to you. Okay. Yeah, this is just the strategy. This is a conservation of current problem for which we can use Kirchhoff's law or junction law. We compute the sum of the currents coming into the junction and the sum of the currents go out of the junction, and then compare these two sums. The unknown current is whether it is required to make the currents into an on-off junction balance. Yeah, it's just what we talk about. And this is the in, this is out. So like the fifth wheel must carry a current of 1A into the junction. Yeah. So if we know if the unknown current is 1A into the junction, a total of 8A flows in, exactly what is needed to balance the current going out. Yeah. So which means our result is makes sense. Okay, let's talk about the batteries and EMF. Okay, and uh, a capacitor, yeah, we know a capacitor quickly runs out of excess charge, but a wire connecting the battery terminals can keep the charges in motion. Yeah, we have already talked about when you like connect to a capacitor, like a parallel plan. Sorry, this is the negative. And yeah, this is negative. With aware and this discharge, like a process is very fast, it is in a very short time. But aware, like connecting the battery terminals can keep the charge in motion. Yeah, if you do this lab, if you like connect a battery to a small bomb and it can last for a long time. When connected to a battery, the wire continues to deflect the compass needle and continues to light the light bulb. Yeah, if we do this like lab, you will see like a light bulb lights and a compass needle deflects, just as they do for a well that discharges a capacitor. Yeah, but it will last longer based on how much the electric potential have in this battery. Okay. Okay, let's continue to talk about how the batteries work. You can see the batteries is now like the capacitor. You can see the capacitors like the parallel plate capacitor. Capacitor, there is the positive charges, the negative charges. If you connect them, yeah, and then the negative goes to the positive terminal. Yeah, but for the battery, yeah, here it's not like this structure. Yeah, there is no like a positive here, there is no negative charges here. And then how it work? Yeah, actually the inner workings of a battery act like a charge escalator between the two terminals. Yeah, the charges are moved from the negative terminals and lifted to the positive terminal. You can see here there are some like charges, and the charge escalator lifts charges from the negative terminal to the positive terminal. Yeah, like the charges goes to the positive terminal firstly in inner the battery, and yeah, the charge Q gains energy. This one, yeah, this we talk about in last class. And if the charges like reach the positive terminal, and then they fell downhill through the wire back to the negative terminal. Yeah, and then the current came, then the current generated. Does it make sense to you? Yeah, this is how the battery work. Yeah, the charge escalator in a battery sustains the current in a wire by providing a continuously renewed supply of charges at the positive terminal. Once the charge reaches the positive terminal, it can flow downhill through the wire until it reaches the negative terminal again. Yeah, we have already talked about that. The flow of a charge in a continuous loop is called a complete circuit. Yeah, you can see this charge from this one to this one to this one, and then goes to here, and then goes and continuously. Yeah, there is a loop, and this loop, yeah, it's called the complete circuit. Yeah. And the charge escalator in a battery is powered by chemical reactions. Chemicals called electrolytes are sandwiched between two electrodes of different material. The chemicals react and move the positive ions to one electrode, the negative ions to the other. Yeah, just like this process may be similar with parallel plate capacitor. A dead battery is one in which the supply of chemicals has been exhausted. Yeah, there are some chemicals inside the battery. If the chemicals used out of them, and then there will be no like the battery will be dead. It cannot work anymore because there is no like electrics like escalator the charge. Yeah, and then this battery doesn't work. That makes sense to you? Okay, by separating a charge escalator establishes the potential difference between the terminals of a battery. Yeah, this potential difference we usually call voltage. If you like buy some batteries in supermarket, and there will be 1.5 volt, 3 volt, and 9 volt. Yeah, this is just the potential difference. Yeah, the potential difference is established by a device such as a battery that can actively separate a charge is called EMF. Yeah, then we talk, you know what is EMF. Actually, yeah, actually the full name for EMF is like a electromotive force. Sorry, it's a electromotive force. Yeah, the short name is EMF. Yeah, like this like represents the maximum potential difference a battery can provide to a circuit. Yeah, this is the potential difference established by a device. Yeah, separate. It's called EMF. This is just like the maximum potential difference a battery can provide. Yeah, the symbol for EMF is this one. Yeah, and its units are volts. Yeah, usually like if you, yeah, just like I said, if you want to buy a battery in supermarket, and usually in the package it noted the EMF 1.5 volts, 9 volt, like 6 volt, like that. Yeah, and this is the symbol for EMF. The capacitor stores separated charges, but has no means to do the separation. because the capacitors just store the charges like negative, positive, positive, negative, but it cannot like there is, but it has no means to do the separation. A charge capacitor has a potential difference, but not an EMF. Yeah, the EMF is just specific for batteries. Yeah. Okay. Like the rating of a battery, such as 1.5 volt, is the battery's EMF. It is determined by the chemicals in the battery. Yeah. A battery with no current in it has a potential difference equal to its EMF. With a current, the battery's potential difference is slightly less than its EMF. We will overlook this small difference and assume this difference, the potential difference is equal like EMF. When we calculate, we usually assume this. Yeah, as a charge Q moves from the negative terminal to the positive terminal, it gains electric potential energy. Yeah, we just like actually we talk about this in last class. If you like a charge moves from negative term to the positive terminal, and this is a potential difference, and this is a charge. So this is electric potential energy. The energy will transform as this charge moves through a circuit element, such as a light bulb, or its way back to the negative terminal. Yeah. Okay, let's review some quick check questions. Yeah, a battery is connected to a well and creates a current in the well. Which of the following charges would increase the current? Yeah, like increase the length of a well, keeping the well the same length but make it thicker. Yeah, use a battery with a lower EMF. Yeah, we know like yeah, making the well into a coil but keeping it dimensions same. Changing the well material from copper to nickel. Actually, I think this one is similar with the question we talked about in the beginning of the class. Like if we want to like increase current, actually the current you can see it is related for the current it is Q divided T. Also, it is depend on the like depend on the like a wire like area wire cross area. Yeah. And if the wire cross area is bigger, and which means this one is right. Yeah. And also like if the charge goes through it like more, and it will be has a bigger current. Yeah, so which means this one is right. Others is now like right. Yeah, so yeah, we will talk about this in next class actually. Yeah, there is equations to represent the current, and the current is related to the like a well area cross area and the some other like features. Yeah, we will talk about later. And okay, let's talk about this one. This conceptual example and potential difference for battery in series. Three batteries are connected one after the other as shown in the figure. We see they are connected in series. What's the total potential differences? Yeah, actually this one is not a difficult one. We can think of this as a three charge escalator, one after the other. Each one lifted charges to a higher potential because each battery raises the potential by 1.5 volt because those three batteries have the same EMF. Sorry. Yeah, you can just consider it as a whole, like the charge isolated from here to here, from here to here, from here to here. Yeah, and the potential difference, the electron potential difference will like 1.5 plus 1.5 plus 1.5. Yeah, so like the total potential difference of the three batteries in series is 4.5 volt. Yeah, okay. Yeah, like I think yeah, there are some like examples in the real world. If you put the For example, the TV remote, if you put the batteries into the remote, you will see the two battery will connect in a series form. Yeah, if you observe it carefully, yeah, you will see that, and then form two 1.5 volt will form a 3 volt battery. Yeah. Yeah, common 2A and 3A batteries are 1 5 volt battery. Many consumer electronics, such as digital cameras, use two or four of these batteries, where wires inside the device connect the batteries in series to produce a total 5 volt or 6 volt potential difference. Yeah, if you do some the real lab, real electric lab on our campus, and you will if you want to get a 3 volt voltage or 6 volt voltage with a battery, you connect two different two three 1.5 volt battery in series, and then you can get 3 volt. If you want 6, then you connect four batteries together in series. Sorry, and then you can get a 6 volt voltage. Does it make sense to you? Okay, yeah, this is what we talk about in this class, and we talk about the model of current. What is a current? Yeah, how to describe and define a current, and also we talk about one application, batteries and EMF. Yeah, and we know that batteries and is a little different with the plate, the capacitors. Yeah, parallel plate capacitors. How is it different? And yeah, this is what we talk about in this class. And the next class we will talk about more about the current, and yeah, yeah, and this is the class for today. Okay. Hope you learn something, and uh, I will see you tomorrow. Okay, see you. Bye.